Hello. Today we're going to talk about extreme values and how to find those for functions of two or more variables. So we start off with a few definitions. For extrema of functions, we talked about these definitions in Calc 1, and now they're showing up again here in Calc 3. You have the ideas of local versus relative, maxima, minima, or more generally, extrema. An extremum is a general term for either a minimum or a maximum. So we see in these definitions that the only difference between where a local maximum or a local minimum occurs is based on this inequality symbol. Do we have the point being greater than or equal to all other points in an open disk in an open neighborhood, or do we have the point being less than or equal to all the other points in the surrounding area? That's the differentiating factor between whether a point is a local maximum or local minimum. And then we can also talk about global maxima and minima. A function may have many local maxima and minima, but at most it will have one global maximum and at most one global minimum, and it's quite possible that it may have neither. The collective general term here would be global extrema. So just a few pictorial examples of this. At a local extremum point will have either a horizontal tangent plane or no tangent plane at all. So these are a couple cases where the tangent plane is horizontal and we have a local maximum and a local minimum. In this case, the tangent plane would not exist because the function is not differentiable at this point, and yet we still do have a local maximum. So a local extremum will have one or the other of these conditions, either a horizontal tangent plane or no tangent plane at all. A few more definitions before we get into the mathematics here. First, we'll start with a stationary point. A point in the domain of a function is called a stationary point if the function is differentiable at that point and the gradient at that point is equal to the zero vector. Also, we have a definition for a critical point. A point in the domain of a function is called a critical point if that point is a stationary point of f, or if f is not differentiable at that point. So it can be either case. So taking these two definitions, we see that every stationary point is a critical point, but there would be some critical points that are not necessarily stationary points. A very important statement for the actual finding of local extrema is the fact that if f has a local extremum at a particular point, then it is a critical point of f. But interestingly enough, the converse of this is not true. Not every critical point corresponds to a local extremum. In fact, there are some critical points that end up being saddle points of f. And so you can see in this diagram here that there would be at 0, 0, 0, there would be a horizontal tangent plane here, and yet it is neither a minimum nor a maximum. And so that's what a saddle point is. It's a stationary point of f at which there is neither a maximum nor a minimum. So to begin finding these, we need to define a new function. And so if we have the function of two variables that has continuous second order partial derivatives, then we're going to define the Hessian of f to be a 2 by 2 matrix of the second order partial derivatives. And so we have h sub f is equal to this 2 by 2 matrix. This is the Leibniz notation for partial derivatives. Here's the Newtonian notation for partial derivatives, so whichever you prefer. But we have the second partials with respect to x in the upper left-hand corner, the second partial with respect to y in the lower right-hand corner, and then the two mixed partials in the upper right-hand and lower left-hand coordinates. Then if we take the determinant of the Hessian, we will get what is called the discriminant. And if I go back to the Hessian there, remember in calculating a determinant, we will multiply upper left hand times lower right hand, and then subtract from it upper right hand times lower left hand. And since these two are the mixed partials, and they are continuous mixed partials, then we know that these two are the same value. And so that's why that we can write the determinant of the Hessian of f, also called the discriminant, should be the second partial with respect to x, the second part times the second partial with respect to y, minus the second mixed partial squared. Whether you do y first and then x, or x first and then y, is not going to matter. Since it's continuous, they're going to be the same. So let's see if we can just find the discriminant. I'm going to move this down here. Hopefully that'll be a little better for seeing the problem listed here. So consider the function f of xy equals e to the 2x times cosine y. Our job is to find the discriminant of f. In order to do that, we're going to need to find multiple partial derivatives. So we can start by finding the first order partial derivatives. So the partial of this with respect to x is going to be 2 times e to the 2x cosine y, and the first partial derivative of f with respect to y is negative e to the 2x times sine y. We can then find the second order partial derivatives, which I have listed for us here. And I'm going to take myself out of this picture for a bit so that we can better see the problems that I have displayed for you on the screen here. So the second order partial derivatives are listed here for the second order with respect to x and the second order with respect to y, and then the mixed partials, which will be the same, are right here, negative 2 e to the 2x sine y. If you'd like to pause the video at this point, you could practice taking those derivatives yourself and make sure that you come to the same conclusions that I have. Once you've verified that you get the same thing, feel free to resume and continue. So the discriminant would be plugging those values in. This is the second partial with respect to x times the second partial with respect to y minus the mixed partial quantity squared. If we multiply through and simplify, we would arrive at this expression, which, hey, notice they have both terms have a negative 4 e to the 4x in common, so we factor that out and you're left with a cosine squared y plus sine squared y, which is just 1. So the discriminant in this case is negative 4 e to the 4x power. And then we could evaluate the discriminant at any particular point that was in the domain, if we so chose. We could say, well, what is the discriminant at the point 1, 2? Well, you plug it in 1 for x and 2 for y. Notice in this case that y has no bearing on the discriminant, so it would just be plugging in the 1 for x, and it would be negative 4 e to the 4th power. So you can find the discriminant then at any value in the domain. And I'm going to wrap up this video at this point. In the next video, I will proceed with showing us the second derivative test.